Hello, students. You are welcome back to the third lesson on sequence. And today we are going to talk about the track and the horizon. Yes. Don't worry, these are just some names to make the lesson more practical. So a visual masterclass of categorizing mathematical sequence by their end point. So today we should be able to determine if a sequence is finite or infinite and how to identify it, or yes. Then write a finite sequence with a clear stopping point and an infinite sequence. Okay, we are going to see when is a sequence finite and when is a sequence infinite and how we can demonstrate it. Okay, now we have scenario A and scenario B. Now every pattern you observe either stops definitely or continues indefinitely. Every pattern. So scenario A, when you read what is there, you see there's a word for first to fifth position. First to fifth position. So the sixth person gets nothing. You see it? And so the positions end at position 5, the fifth term. Okay. In scenario B, Amma saves 5 cities a week. So first week, second week, and third week. The question says that she saves 5 cities a week. So it is true that she's going to save in the fifth week, in the sixth week, in the seventh week. And so her savings per week is continuous. Okay. So this two gives us a clear difference between sequence. One sequence stops, another sequence goes on, is continuous. Good. So the two distinct categories of mathematical sequence. All right. So by definition, one has a fixed and countable number of terms. The other one has no end and goes on forever. The first one has a definite last term. The other one has no last term. The second one, the first one, there's absence of dots. The other one ends with the ellipsis symbol. Now, this is what we call the ellipsis symbol. Okay, the 3 dots. It demonstrates that the sequence is continuous. Okay, yes. But for this sequence, it ends. It ends. All right. So let's talk about the finite step. Finite sequence have a measurable length and a terminal boundary. Okay. The first term is 3. Sorry. The first term is 3. And the last term is 23. So the length is 6 term. Okay. we know exactly where it ends. Okay. Good. Infinite set. We have the first term, we have the fourth term, but we do not know the fifth, the sixth, and the seventh term. Okay, so we can never write the last term because a last term does not exist. And the ellipsis symbol demonstrate that. So we have two types of sequence: finite sequence and infinite sequence. Okay, so this is a mathematical demonstration of the ellipse sign, the ellipsis sign. So the symbol demonstrates that it moves on. Okay, so the three dots is non-decorative. They carry a specific mathematical instruction. So we write a three dots to demonstrate that the sequence travels on. Thank you. Okay, so another demonstration here. Correct sequence. Correct infinite sequence. Okay, we have three dots. We have correct finite sequence. You see, you can put the dots in the middle, the three dots in the middle, and write the final term. What it means that it's from 1, the values are 1 to 250. Okay, this is a finite set, but this is the incorrect one. Yes, this is an incorrect or false infinite. Okay, when a prompt asks for the first 6 sequence or for the first square numbers, okay, so this is correct, it can move on. But if the question says the first 6, after you get here, you don't have to add the dots because it is saying the first 4, the first 5, the first 10. These are finite sequence. So do not add the dot to it. Okay. So let's talk about some common misconceptions. One is the length myth. So if a sequence has, let's say, 1,000,000 terms, it is infinite because it is too long to count. No. Okay. It doesn't matter how many terms, as long as we know that the end term, it is finite. So even, look here, even 1,000,000 term is finite if it has a stated endpoint. Good. And the next misconception is the missing promise. Writing 100, 90, 80 is enough to show an infinite sequence decreased by 10. Nope. If you write this to show an infinite sequence, no. Okay. If this is finite, if you want to show infinite, you have to then bring the ellipsis symbol. Okay, ellipsis symbol. Okay, so let's look at this pattern. So there is savings. Okay, there's money savings in the account. So the mathematical pattern is identical, but the real world constraint dictates the notion or the notation. If it stops, remove the dot. If it runs forever, add the dot. So let's say I withdraw the funds on year 4. It means the interest does not go, it ends in year 4. Okay, this in real life, the term ends in year 4. My savings ends in year 4, or my interest ends in year 4 when I withdraw. But you remember, sometimes we have compound interest. Okay, if you learn compound interest, it can go on and on and on indefinitely, as long as you wish. And so you can use the ellipsis symbol to demonstrate a compound indefinite interest. Okay, so there's a brief diagnostic framework. All right, question 1. Does this have a clear stated last term? Yes. If yes, it is finite. Does it end with an ellipsis without a following term? If yes, it is infinite. Are there dots in the middle, but a number anchored at every end? For example, 1, 2, dot, 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 then 50. It is finite. Okay, please pay attention to this. All right, so this is how far we've come. Lesson 1, lesson 2 taught about naming and patterns. And lesson 3, we've established finite and infinite sequence. All right, we're going to move on to lesson 4. See you there.